Hey class, and welcome to section 3 of lighting and lighting efficiencies. This topic will be specifically on lighting fixtures and different types of lights that you might encounter on various building audits. So let's start off with the basic example. We've talked about this already, but the Edison bulb or incandescent light bulb, where you're running an electric current through a tungsten filament. Now this is surrounded by a glass envelope to prevent the filament from corroding or being touched or damaged in any way. This is how light bulbs go out, is that filament eventually fails. But there's nothing special inside this vacuum seal. It's just air, but it's protected from the outside. These are great. They emit a lot of energy, but not all of that energy is in the visible spectrum. So let's go back to lecture 1. We talked about the amount of energy that we're getting from the sun. Sun's great. But a majority of that energy is emitted in the visible spectrum, but there's a whole lot of extra energy that's invisible to us, that's in the infrared spectrum. Now that's relevant because a similar thing happens with an incandescent light bulb. So we run some electricity through this wire, we get some energy out in the visible spectrum, but most of the radiant intensity being emitted, it's going to follow this sort of profile in terms of the wavelengths that are emitted, kind of like Wien's displacement law. This follows basically emissions from a black body, kind of like the sun, and it's going to peak at a particular wavelength based on the temperature running through this thing. And that peak is actually outside of the visible spectrum. It's in the infrared range. What does that mean? It means we're emitting a whole lot of heat as we're running electricity through this, which is great if you're trying to keep something warm, like a heat lamp. Not so good if you're trying to make things bright, emit visible energy. And, we talked about, changing the color of light a little bit. When you start with just a little bit of current through here, it's kind of that dim reddish glow. As you put more energy into it, it gets brighter, so this intensity gets higher, and it appears whiter. What's happening there is we're starting to see more wavelengths in this shorter wavelength spectrum, because we're raising this whole profile as we put more energy into this, as we're drawing more power. It's not that we're moving this curve horizontally, we're not changing the wavelengths emitted, we're just producing higher intensity wavelengths. So even though this is getting brighter, it's just because we're lifting this curve up a little bit, but the majority of what we're emitting is still going to be heat, right? Not necessarily visible light, which is a problem if what you're trying to do is use watts to produce visible energy. One way around this is to change the temperature of this emission a little bit, and that's where halogen lights come in. Halogen lights, here's an example of one. They're basically another version of an incandescent bulb, except instead of just having air inside of this guy, we evacuate it out, and the tungsten filament is now embedded inside of it like a halogen gas. That has some interactions so that the tungsten doesn't wear out as quickly. You get kind of this sort of evaporation effect, so less corrosion on the filament, they can last longer. But that means it needs to operate at a higher temperature. So generally the lights are brighter because it's more intense, more lumens being produced, but still a majority of those are going to be in that infrared spectrum, and we can't actually see a lot of it, right? Once again, just raising the amplitude of this, but yes, we're getting some more in the visible spectrum, but a lot of it is still going to be in that form. So not super efficient, but longer lasting than a conventional incandescent. Fluorescents operate a little bit differently. These are your typical hallway, creepy, flickery tube ones, right? The ones that you really don't want to use as a lifesaver because they've got mercury and bad stuff in them. Now there are CFLs or compact fluorescents, but they operate on the same principle. That principle is basically running an electric arc through a plasma. So these tubes are vacuum sealed, and you've got kind of some suspended mercury and maybe some argon in there. And at either end, you're going to have some cathodes. And when you run an electric current through that, it's going to create this electric arc, which is great. It produces a lot of energy. Most of that energy, though, is in the ultraviolet spectrum, which we can't see. Maybe the bees can see that, but we certainly can't. So the other thing that's inside of these tubes are phosphors. And these phosphors, sometimes they're referred to as fluorescent powders. I guess you can see where that name comes from now in terms of fluorescent lights. These phosphors basically transfer that UV energy into the visible light spectrum. But it's not a perfect translation. You get some kind of peaks in different wavelength colors. And you've got some very interesting electrical requirements as well. So because we want to be regulating this electric discharge at all times, you need a way to manage that off of an alternating current. And that's where a ballast comes in. I've got a photo up here at the top of a ballast. And so sometimes if you hear like a buzzing or the lights flickering, people will say that's a bad ballast. It means maybe the tube is still good, but the part of the bulb that's actually, or the part of the light that's actually regulating the current to maintain that arc is going out of it. And so sometimes you need to replace ballasts in addition to replacing the actual bulbs or lamps. There's a few different kinds. They're referred to in terms of their diameter. So there's T12s. Those are very thick. I believe they're in reference to millimeters, but don't quote me on that. So there's T12s. T8s are a little bit thinner, and T5s are even thinner than that. T5s, I think, are mostly used for like aquariums. They're not often found in buildings. What you will find a lot of are T8s, and those can range in efficiency, but pretty much any T8 is better than a T12, and T12s are rapidly being replaced. I don't think they're allowed by code anymore, but you might be able to find them at like Habitat for Humanity or a Second Chance store because people are trying to get rid of them because they're no longer useful in new buildings. So that's one thing to be aware of. As I mentioned, they emit light at kind of odd wavelengths. So on the left here, you can see they peak at a couple of different wavelengths in here. It's much harsher than that kind of smooth curve we were seeing with, say, an incandescent lamp, or even a halogen, which is just an incandescent at a slightly different temperature. Right? Those are much more smooth, conventional black body radiation being emitted, whereas a fluorescent, it's relying on a different set of physics principles, right? These phosphors that are converting that UV energy from that arc out into the visible spectrum. And that can lead to kind of some odd colors, and why people aren't necessarily huge fans of fluorescents can also make them somewhat difficult to dim or change the color of. Another form of relying on that fluorescent technology of creating an arc are sometimes referred to as high intensity discharge, HID lights. Two examples of these are halide and sodium lights. Sodium would be the old street lamps, the really yellowish ones. Once again, relying on kind of this physics of phosphorescence, whereas halide lights are much brighter. These things can take a while to warm up. They can also take a while to shut off. There's not really dimming. So these are your stadium lights, and halide are much more widely used than the sodium. It's a brighter, more pure light. Unfortunately, they do have certain issues. For example, if these are in a warehouse and you were to walk in and you wanted to have them on occupancy sensors, if, like I said, if there's a warm-up time for these to actually hit that emission range in the visible spectrum, for that temperature to rise enough and that chemical reaction to start occurring, that arc. They also rely on certain ballasts as well. So not only do you have to replace the bulb if it wears out, you might have to also replace the ballast. All right, so let's move on from those and talk about the cool new kids on the block. These are LEDs, light emitting diodes. These rely on a principle known as electroluminescence. It's a cool term. The idea is that these are essentially semiconductors, and as you run an electric current through them, they emit photons in a particular wavelength. So you can kind of program these to be a true blue or a true red light, not just some sort of red colored lens that goes over a light, which is what we used to do with, say, like an incandescent. It can also be paired with particular phosphors as well. So you get some of that UV energy out from that LED, and that UV can then activate some phosphors, kind of like a fluorescent, to shift the color and energy spectrum a little bit. So let's look at the spectral distribution of a few different kinds. So we started off talking about incandescents or halogen lamps, right? And this is looking at all wavelengths. What the human eye can actually see is probably starting here around the 300, 400 wavelength range up to maybe the 800 range. I'm afraid I'm an engineer, not a biologist, so I might be missing a bit. But generally, we want to be looking in here. Now, sunlight is great. It covers that full spectrum, right? But an incandescent, we're just catching this first part of it in terms of emissions. A metal halide, one of those fluorescent systems, has a profile that's more suited to the human eye, which is great. Up here is just kind of another way of looking specifically at the visible spectrum and the colors that we're used to. So incandescents, once again, we're just getting the first part of that curve. The rest of the emissions are occurring outside of the visible spectrum. So we're losing a lot of that energy if what we're trying to do is produce light. And LEDs, depending on what type you have, we can kind of dope these semiconductors with different elements to produce wavelengths in kind of different color spectrums, which is really neat. And that technology is still advancing a lot, and they're coming down in price a lot, which is great. The other thing to be aware of, and I mentioned this before, is kind of directionality. So we have an incandescent light bulb. It's producing light basically in every direction, right? Candelas flowing everywhere. With an LED, because it's operating on kind of a different physics principle, those waves are emitted basically straight out from that little semiconductor chip up. And that's great for spotlights, or really trying to profile a particular section on a building, or use in a flashlight. But what you might have unintentionally are maybe some shadow effects. Like if you were to put your hand in front of that, you're going to be blocking a lot of that light. This is important in manufacturing and industrial processes, because a lot of incandescent and as well as halide lights have been replaced with LEDs. Now that saves a lot in terms of energy because LEDs are much more efficient at producing visible light based on the energy input to them. The downside being that the old-fashioned light bulbs, you had a lot of illuminance in the space, right? Because you had a lot of reflected light because those wavelengths were going everywhere, and they'd be bouncing off. Whereas with the LEDs, it's much more focused. And so if you are a plant worker and you're assembling some part and then suddenly you lean over it and block the light that's coming down from above, you're going to cast a shadow over whatever you're working on. Or if you're working underneath a tractor, or there was, what was it? It was a fire station that our office was recently auditing. They had replaced them with LEDs. And because the light was so directional now with the LEDs, it was pretty much black underneath the fire engines, and people had a really hard time. They had to wear headlamps working up underneath the cars. They didn't used to, because they used to have halide lights which sent wavelengths off in every direction. So just be aware of the directionality of how these lights are installed, and there's not necessarily a one-to-one replacement in terms of lumens, right? That's why we want to go in and measure the amount of light being cast onto a particular surface with illuminance, and we'll go over how to measure that in the next lecture. So just to recap, we went over incandescence, Edison bulbs, as well as halogen, fluorescence, either the tube or the high intensity discharge, which would be your stadium or street lights, which rely on a sodium or halide gas as opposed to a mercury, as well as LEDs or light emitting diodes. Hope that was informative, and look forward to seeing you guys next lecture.